Okay, today I'm going to go over a multiple part problem or combining motion in 2 dimensions as well as forces in 2 dimensions. So this is a problem that was imagined up by a student, and you start off with someone being launched, or something being launched at 10 meters per second at 30 degrees. And this is the catch, is this goes up and then comes back down and wants to hit a ramp at 45 degrees down here. So when it hits this, the velocity wants to be at 45 degrees also. So 45 degrees maybe right here, 45 degrees. This would be 45-degree angle. And this is, let's say, a 5-meter high ramp. And at the bottom of this ramp, it transitions. That would be a tough transition to actually go through. Not something that you'd want to experience yourself. And then they'll slide along here. This happens to be frictionless. Mu is equal to 0. Over here, maybe it's a person launched out of a cannon. Let's just call this person Andrew. So Andrew gets launched out of a cannon, lands on this ramp, and then skids along this surface right here, which the student described as being sandpaper. Again, not something you'd want to experience, with a coefficient of kinetic friction of 0.5. So we don't know what the height is above this 5 meters. We don't know what this, we'll call this delta y, and we also don't know what this distance right here is. We'll call this delta x. So we're trying to find where we have to position this ramp so that when the Andrew is launched out of his cannon at 10 meters per second, where this will end up. So we're first dealing with the projectile problem, and so we break our projectile up into its 2 components. So this is then our v naught x, and this is our v naught y. I'm just going to solve for the v naught x and v naught y right up here. So that's going to be v naught, and this is the adjacent side, cosine theta, and this is v naught sine theta, the opposite side. So then I'm just going to plug in. I end up with 10, and here we have cosine theta of 30. It's the adjacent side, the longer of the sides of the triangle. Although this isn't drawn very well, I would emphasize that you try to draw your triangle angles to scale. It can actually help you kind of see which is the longer side and which is the shorter side. This is the longer side, being root 3 over 2, which then we could simplify this a little further. 5 root 3. This is going to be 10, and sine of 30 is a half, the shorter side, not 10 and a half. And then this equals 5. These are meters per second, meters per second. Okay, so as I talked about in class, if I were to draw a line straight across from where it was launched, the angle that we have right here is at 30 degrees. Right at this moment, it's at 30 degrees. So it's got to be some distance below that we actually reach 45 degrees. That is to say that the y component has to continue to increase so that it will equal the x component. So we create a 45-degree angle by having the x and y equal to each other. Well, we know that there is no acceleration in the x direction. That's 0. So therefore, there is no change in velocity. So therefore, the velocity initial in the x direction is going to be equal to the velocity of the final in the x direction. So this is equal to v naught x, which is equal to vx, which is equal to my 5 root 3. I didn't mess this up. This is 5 root 3 meters per second. Okay? So if this is one side of the triangle, that's 45 degrees, the other side has to be equal to that, so therefore the Vy has to be equal to this 5 root 3. And hopefully you guys caught that. So if now we're going to try to find out what the final velocity, the magnitude of the final velocity is. The magnitude of the final velocity is just using Pythagoras. So it's this term squared plus this term squared. So this term squared is, let's see, we take 3 squared, the square root of 3, take the square of that, that's 3. 5 squared is 25. 25 times 3 is 75. And we do the same thing to this term, which is the same term, so it's 75 plus 75 is 150. And we take the square root of that. If we remember, a squared plus b squared equals c squared. Solving for c, you take the square root of both sides. So this is equal to the square root of 150 meters per second. All right, that's the velocity that's going to be when it hits the ramp. But where do we place the ramp? Well, we have to look at, let's say, the y direction and look at the projectile. What do I know in the y direction? I know that the initial velocity in the y direction is equal to 5. I know that the final velocity, and now this is, you got to be careful here, the final velocity in the y direction, oh wait, this is x, and this is, oh, I did this terribly over here. So this ends up being y, and this is y, but the same logic works. Oof. I'm not going to bother redoing that because these are equal to each other, but this is the y direction and this is the x direction. Vy over here is then going to be equal to negative, because it's in the downward direction, 5 root 3. My acceleration is equal to negative 10. My time, I don't know. My y final, I'll say that's 0, and my y initial is, I don't know. Okay, so I will pick on, let's see, I want to know this height. I don't have time. I don't know what the initial position is in the y direction. So I will use v squared is equal to v naught squared plus 2a delta y. So we end up with, let's see here, this term squared, right? So that's 75. We've already determined that from over here. And then 5 squared, I'm going to pull that over to the other side, minus 25. So I've just pulled this term over to this side. And then that's going to be equal to 2 multiplied by negative 10 delta y. Does that work out? Yeah, I think so. So I end up with 50 all over 20. And this is a negative because this is a negative value. I bring that over. That equals my delta y, which makes sense because I'd have a change in my y that would be negative. It starts higher and goes lower. So this delta y is equal to 2.5 meters. So that means that this delta y is 2.5 meters. It goes down, so this is 2.5 meters up here. And the top of the ramp, we're going to say, is at 0 meters. Okay, so now what is the x direction? So I look at the x direction. Let's see here. What do I know? What don't I know? V naught x is equal to Vx, which is equal to 5 square root of 3. We end up with a is equal to 0. T is I don't know. X initial is 0. X final is what I'm trying to find. Let's see. That's about all we have. So I'm going to choose to find time first. So I'll use x. Whoa, boy. Can I find the time in this? No, I actually have to go back to the y. So I have to go back to the y direction to find time. And I'm going to say v is equal to v naught plus at. And this is in the y direction to find time. So that is how long does it take to go from a positive 5 meters per second to a negative 5 root 3 meters per second. So negative 5 root 3 is equal to 5 minus 10t. So this ends up being 5 root 3, negative 5 root 3 minus 5 over negative 10 is equal to t. So I found my t, and I don't have a calculator with me right now, so but this is what my value of t would be. And so then I go over to my x direction here, and I end up with x is equal to x naught plus v naught xt plus 1/2 at squared. This is 0. This is 0. X is then equal to my 5 root 3 multiplied by my t, which is up here. So I plug that in and I can figure out what my x is. All right, so the second part of this problem is now Andrew has landed on the top of this frictionless ramp. So I will pull some of that information to a ramp now. So here I'll blow this up a little bit. So this is 5 meters high, which was given in the problem statement, and it's a 45-degree angle. So that means this is 5 meters high. And I know that I'm coming in, we solved this from before, this is, the velocity is equal to the square root of 150 meters per second. And if you're more comfortable, that's about 12.25 meters per second. And it's frictionless. So let's see here. We have Andrew, which maybe he's put in a box and he's going down this ramp. We need to figure out what the length of the ramp is, so that's 5 squared plus 5 squared. Take the square root of that, so that's a square root of 50. All right, that's my distance along the ramp itself. Because that's, so let's see, he lands on the top of the ramp and then he'll continue to accelerate down the ramp. So let's draw my forces. So I need to figure out what that acceleration is. I divide my forces up into the y direction and the x direction. All right, it's getting a little messy. I'd want to draw a bigger picture. I have a lot of values here. I have the distance as well as my forces on here. So ideally, I actually would just draw a sketch with my forces, because that's all I'm worried about. That's all I need to find the acceleration. Doesn't matter how long the ramp is. Doesn't matter what the initial velocity is. All I need is these forces. So why don't I pull out a free body diagram to try to isolate that. So I end up with Fn, Fgy, Fgx. And so it's accelerating in this direction. So the only force that's accelerating is Fgx, so I'll sum the forces in the x direction is equal to ma. And I don't have friction force, so I don't have to worry about this Fn. So this becomes fairly straightforward. Fgx is the only force that's going to accelerate my object, Andrew. And so then I end up with mg, this is my angle up here, 45. It's a 45, so I could do sine or cosine, but if I'm going to follow my rules and make sure that I'm doing this correctly, if I had a different angle, it's going to be sine theta is equal to ma. Cross out my m's, so then I end up with, let's see here, my a is just equal to 10 multiplied by root 2 over 2, which is equal to 5 root 2. Right, 5 root 2 meters per second squared. All right, so now what? Now I take this and I apply it to my, it's actually linear motion along here. So it's in just one dimension too. So I'm only going to deal with the x direction. I want to figure out what the final velocity is down here before he transitions to the sandpaper horizontal plane here. So to find that final velocity, I am going to pick on the x direction. It's the only direction I have to worry about. And I could list this down here. I could say that x initial is 0, x final is equal to the square root of 50. I could say that v initial is equal to the square root of 150. I could say that v final is what I'm trying to find. My acceleration is equal to 5 root 2. And my time is equal to, I don't know. And it actually doesn't matter because I can find an equation that's independent of time. So I end up with my v squared is equal to v naught squared plus 2a delta x. This is the equation that's becoming our friend for these types of problems. And so I'm trying to find this, so I end up with v squared is equal to v naught squared, so that's 100, the square root of 150, so that just ends up being 150, plus 2 times a, so that ends up being 10 square root of 2, and my delta x is the square root of 50. All right. So this then ends up being v is equal to the square root of all this 150 plus 10 square root of 2 square root of 50. All right. Now I don't have a calculator, but this would work out, and it would be something in meters per second. And then finally, I have the situation where Andrew has now reached the bottom of the ramp. Maybe I'll actually draw a little Andrew here. And he's sliding along this sandpaper. Hopefully he has thick jeans on. And he's going to eventually come to rest, and I want to know how far he goes before he comes to rest. I'll call that delta x. So if I were to draw a free body diagram, I'd have Fg, Fn, and FF. All right? And so it's the FF that's accelerating, so we have to find the acceleration again. So you end up with the sum of the forces in the x direction is equal to ma. The forces are FF is equal to ma. This FF is equal to mu Fn. And in this case, Fn is equal to Fg. It wouldn't be in this case. It wouldn't directly be equal to Fg, right? It would be equal to Fgy. But in this case, because it is traveling horizontally, you don't have to break up your Fg into the x and the y. This just ends up being mg is equal to ma. Cancel out your m's. Doesn't matter what the mass of Andrew is. And then you end up with a is just equal to this 0.5, which was given in the problem statement. That would be kinetic. Is equal to multiplied by g, which is 10. So 0.5 times g is 5 meters per second squared. Okay, now you want to figure out how far he goes so that you know the acceleration. So I would look at this again as x direction. What do I know? X initial is equal to 0. X is what I'm trying to find. V initial is equal to whatever this is. So this ends up being my V initial. So I know this. This is a known. My V final comes to rest when he stops is 0. My acceleration I've determined as, now this is important, -5. It's going to accelerate in this direction. The net force is in this direction. All right, and I don't know time. Again, I don't need to know time because I'm going to use this equation again. V squared is equal to V naught squared plus 2a delta x. 0 is equal to whatever that V naught squared is. It's a known value, right? We know we can put it right in there. Minus 10, -5 times 2. And I'm trying to find my delta x. So my only unknown is my delta x, so I can solve for delta x, and so I can figure out what that is. All right, that's it. A lot of work, a lot of steps in here. But as long as you kind of keep these straight, you can actually come up with an answer. You can take on a kind of complicated multiple step problem with just the kind of understanding of breaking your vectors up into two different components, using Newton's second law to find your accelerations, use your equations of constant acceleration to find out what your final velocities and distances are, and you can solve this type of problem.